Hello and welcome. Today's webinar is Improving Recreational Trail Accessibility with a Volcanic Ash Treatment. My name is Lacey Friedley. I am the Communications Coordinator at Portland State University's Transportation Research and Education Center. TREC leads the National Institute for Transportation and Communities, the University Transportation Center funded by the USDOT. NITC consortium members are, in addition to PSU, the University of Utah, University of Oregon, University of Arizona, University of Texas at Arlington, and the Oregon Institute of Technology. NITC's research priority is improving mobility of people and goods to build strong communities. Our presenters today are CJ Riley and Ashton Greer of Oregon Tech. Dr. CJ Riley is a professor and graduate program director in the Civil Engineering Department at the Oregon Institute of Technology. He is a fellow of the American Society of Civil Engineers and has taught solid mechanics and structural engineering for over 15 years with a particular focus on hands-on demonstrations, field investigations, and active learning. Dr. Riley is a licensed professional engineer in Oregon with professional experience in highway bridge rating and design, as well as vibration-based structural health monitoring. Dr. Ashton Greer is an assistant professor of civil engineering at Oregon Tech with a focus on water resources. She is particularly interested in Western water management and is passionate about utilizing remote sensing and spatial analysis techniques to develop solutions to complex water issues. Before diving into the presentation, I'd like to let you know about some other upcoming webinars. On March 15th, Philip Stoker of the University of Arizona will present on planning and development in gateway communities post-COVID. In May, tentatively scheduled for the 18th, Surisha Katuri of PSU and Taylor Lee of the University of Texas at Arlington will present a pedestrian behavior study to advance pedestrian safety in smart transportation systems using innovative LiDAR sensors. On June 8th, Rebecca Malden, Stephen Mattingly, and Rupal Parekh of UT Arlington will share research on transportation resources and behaviors among older immigrants. Today's presentation will be about 40 minutes long, then we will have 15 minutes to answer your questions. During the presentation, please submit your questions via the Zoom Q&A. After the webinar, you will receive an email with a link to the video recording and presentation slides. If you are tracking professional development hours, this webinar is eligible for 1 hour of continuing education credit. A certificate of completion will be posted on the event page within 24 hours after the webinar ends. And with that, I will turn it over to our presenters.
All right, thanks a lot, Lacey. I appreciate the introduction. I'm CJ Riley. I'm here with my colleague Ashton Greer, and we're going to talk to you about a recreational trail improvement that we did with volcanic ash and with the goal of improving wheelchair accessibility. We're both at Oregon Tech, and we worked with a group called the Klamath Trails Alliance on this project, and of course NITC was the funding agency. We're going to start off with a poll of the audience. We're interested in having you picture the most wheelchair accessible recreational trail you can think of. Think about where that is, if it's a specific place you've been to, and then what makes it great. Or if you can just think of features that you would think would be appropriate for wheelchair accessibility, you can drop those in the chat as well. So we should have the chat open now, and you should be able to answer there. And I'm seeing wide walkways or travelways, clear borders, clear edges. That's great. Thanks for that. A smooth surface. Absolutely. Seems like the right thing for wheelchairs. Someone telling us there's a great trail near Hilo, Hawaii to a waterfall. Yeah, so the location is always a bonus as well, right? If the trail leads to something that you want to see. Right? No hills, low slopes. Yeah, I think these get at a lot of the points we want to make in this presentation. So I'll start with that, and we'll continue. We are going to go through a few things here. We'll have the project goals that I'll outline, tell you about our location and ash sourcing, talk to you a little bit about our previous research and the motivation for this particular project. We'll tell you some of the particulars of cementitious and pozzolanic reactions, tell you about embodied carbon and sustainability components of this project, and then get into the meat of it with the batching and processing and logistics and how we pulled off this trail implementation. We'll tell you about the ash recipe, what was the binder that we used. We'll tell you about its implementation on a trail we call the GeoTrail, and the performance after we conducted the implementation. And then finally, we'll tell you a little bit about some of the future work that we're going to be doing at Oregon Tech as a result of this project. So the project goals, this was an implementation project. The requirement was that we had done some prior research, and there are a number of projects prior that I want to tell you about. It had to be a field scale implementation. We chose a section of trail nearby the campus that had good slopes. And the big issue for us was really practical issues. A lot of the prior work had been done. We were working on material handling, batching, mass handling of materials, how we would apply the material, and then finishing the trail surface. So the big goal was to improve the surface firmness and stability. And someone mentioned smoothness and size. We were constrained on size, but certainly roughness or smoothness was something we were considering as well, and I'll talk about that. Ultimately, we wanted to create a platform for long-term performance studies because this gave us an opportunity to do so on a fairly long section of trail. And because Oregon Tech is really dedicated to our students' learning, we wanted to engage them throughout the process. So you'll see them in a lot of these slides as well. I'll hand it to Ashton to tell you a little bit about where we are.
Thanks, CJ. Yeah, so I thought I'd provide a little bit of a spatial orientation and context for our study area. So Oregon Tech is located in Klamath Falls, which is in very southern Oregon. And for those of you not familiar with this region, we're kind of a rural community in a high desert ecosystem with access to a lot of surrounding nearby natural resources. So you can see that we sit just east of the Cascade Mountain Range and about 50 miles south of Crater Lake National Park, which you can probably see most clearly on the right-hand side of the map here. So Crater Lake is an especially unique feature in Central Oregon, particularly for its interesting geological history. So Crater Lake is not, in fact, a crater, but a caldera formed by the eruption of Mount Mazama about 8,000 years ago. So this is a really cataclysmic eruption that kind of fundamentally shaped the geology of the Pacific Northwest. So not only did it leave us with the deepest lake in the United States at almost 2,000 feet, but it enveloped the entire region in a layer of volcanic ash. So you can kind of see the general extents of that ash layer in the bottom left of this slide. And for context, you can see how it compares to the extents of the Mount St. Helens eruption in 1980. So this eruption generated about 42 times the volume of ash that one did. This deposit of ash, which we refer to as Mazama ash, is now a persistent geologic layer throughout the northwestern US and up into southwestern Canada, with depths up to 6 inches in some places. So like other mineral deposits, Mazama ash can be extracted, and there's some operations who've begun to extract Mazama ash for commercial use. One of these operations currently retrieving raw ash material is Beaver Pumice Mine, which is located just south of the town of Chemolt, Oregon. So this is about 10 miles northeast of Crater Lake, and it's a really easy trip up State Highway 97 for us and takes about an hour to get to from Oregon Tech. Beaver Pumice Mine produces pumice products from a quarry in Beaver Marsh, and you can see some of their operation in the photos on the next slide. So their processing can involve separating these volcanic materials by gradation or even grinding those materials down to achieve a desired size. They currently primarily market their products for small scale agricultural applications, but they're interested in exploring potential other uses of their ash products as well. So on the bottom right, you can see the bags containing about 7 cubic yards of raw ash material that were generously donated to us by Beaver Pumice. And we planned to use this material to treat a segment of the trail, of a trail adjacent to the Oregon Tech campus. So the Geo Trail is an approximately 2-mile hiking and snowshoeing trail just east of our campus. It was completed in 2016 as a collaborative effort between Oregon Tech, the nearby Sky Lakes Medical Center, and Klamath Trails Alliance. So again, that kind of local nonprofit who helps build and maintain a lot of our local trails. It provides access to some really scenic terrain, and while it's used from people all across the community, some of the more frequent users are Oregon Tech students, medical center patrons and employees, and residents of the nearby Crystal Terrace retirement home. So we identified a 0.2-mile section of the trail on which to apply our surface treatment. You can see here, and we chose this section for one, because it was really easy for us to access immediately adjacent to campus, and also because the slope of this section is already within ADA regulations for walkways. So having set up a bit of context for the location of this study, we'd like to take the time to recognize that Oregon Tech resides on Klamath, Modoc, and Yahooskin land, and we think it's really important to acknowledge that as we continue to engage in this work on this land and with resources that are being extracted from it. So I think a deep motivation of this work is to responsibly steward access to this land so that it can be enjoyed by everyone. So the clip on the left shows the original Geo Trail surface, which is a fairly uniform 3/8-inch aggregate. While it's relatively smooth, you can see the rutting after wheelchair use, and the looser aggregate results in more rolling resistance. So the right-hand clip shows less rutting and kind of associated less rolling resistance from the wheelchair users. So we're going to talk about everything that happened between this before and after video, starting with CJ talking about some of the previous research and motivation behind this project.
Thanks, Ashton. So here we have 3 different studies. The first one on the left was a preliminary study that attempted to use the Mazama ash as an improvement for unpaved roads, in particular levees in the area that are composed of poor soils and often have roadways across them. A second study by Matthew Sleep, one of our former colleagues, tried to focus in on accessibility improvements and really started us thinking along these lines. There were thousands of mortar cubes cast and broken in this study that really gave us a good idea of how this ash performs when it's combined with different cementitious materials like Portland cement, like lime, and other products. Our study attempted to scale up their test patches that are seen in the photo in the center and apply this to a 0.2-mile section of trail so that we could better assess the performance of the material on a longer trail. So that's the study we're going to tell you about now. A lot of this is built on a study called the National Trail Surfaces Study that was conducted in 2014 that focused on 11 different types of materials on trail surfaces in Indiana. And 3 of them were limestone-derived aggregate trail surfaces, fairly natural, but different gradations. 8 others were commercial topical products. And in the end, the topical products didn't perform as well. They generally left crusts or they failed at the edges. And so the natural products became the real recommendation. The group also surveyed a number of trail managers around the country in different regions, and found that in general, those trail managers would recommend as deep as possible an aggregate base, and then a finer binding material at the surface. And that ultimately trails composed of primarily aggregate surfaces were easier to maintain. Oregon Tech research, though, was really focused on trying to bind the top surface and make improvements in the firmness and stability of that surface. So commercial products were also tested and with similar results. And the long-term strength gains for the ash cement binders appeared to improve over time, giving us an idea that this really held some promise. Some of the details of that work are shown here. This is compressive strength on the y-axis versus the ratio of ash to Portland cement on the x. As I said, thousands of mortar cubes were cast. They effectively showed that the arrow, the upward pointing arrow on the left, tells us that pozzolanic activity is happening, that the mortar cube would strengthen up to 28 days, the dark circles, and beyond that would continue to gain strength, which is indicative of pozzolanic activity. It was clear and expected that the strength of those mortar cubes would drop as the ratio of volcanic ash increased. And so we identified a sweet spot here at right around 50-50 ash to cement in the binder that we would use. Some of the other issues, though, that this study found were that the fineness of the raw ash was not as fine as necessary to characterize this as a class N pozzolan. So some grinding or processing would be necessary to use it that way. And then attempts were made to apply this as a topical treatment to some ash surfaces, and issues around clogging were identified. And so those were some of the challenges that we knew we were getting into when we started our work. I'm going to hand this back to Ashton to tell you a little bit more about materials, and then I'll come back and tell you some more about how we developed our batches.
Great. So when we're thinking about these materials, I think it's important to consider the energy and resources required for cement versus natural pozzolan production like Mazama ash. So Portland cement is manufactured by extracting limestone, crushing it and grinding it down to a much finer material and heating it in a kiln to form a substance called clinker. That clinker is then cooled and ground to an even finer powder that we can then use as Portland cement. Portland cement is often shipped across long distances to reach its destination. And so this is ultimately a really intensive process that has really extensive embodied carbon costs. Mazama ash is what we would consider a natural pozzolan, and these often require significantly less processing. So once extracted, they might only need to be crushed or sorted. And as a substance that's naturally occurring across the Pacific Northwest, it typically requires far less shipping distances. Even though Mazama ash isn't present across the entire US, there are different types of naturally occurring pozzolans across the world. So ultimately, this can mean far less embodied carbon tied up in natural pozzolan usage. Sleep and Masley evaluated the embodied energy associated with production of some common combinations of various cementitious mixtures, and found that Portland cement had the greatest embodied energy, while mixtures incorporating natural pozzolans tended to have much lower embodied energy. And so you can see our combination of ash and Portland cement there on the right. So hydraulic cements like Portland cement become adhesive through a chemical reaction between the dry ingredients and water. Hydraulic cements are essentially made up of a mixture of silicates and oxides that react directly with water to form the hydrates calcium silicate hydrate and kind of secondarily calcium hydroxide or lime. These compounds act as adhesives that bind other materials together and gain strength over time as they cure. Pozzolans like Mazama ash are siliceous materials that in the presence of Portland cement and water will basically react with the calcium hydroxide released by the cement hydration to form compounds possessing cementitious properties. So alone, they pose little to no cementitious value at all, but in the presence of cement, they can create reactions that continue adding strength for even longer periods of time than cement alone. And there's a lot of historical context for using natural pozzolans in infrastructure applications. So there's historical record of natural pozzolans being used to construct structures as early as ancient Greece. And notably, Roman concretes consisted of a mix of volcanic ash, lime, and water, and many of their roads and structures still exist today, 2,000 years later. So this durability is obviously of significant interest to concrete researchers, but somewhat remained an enigma. However, a recent MIT study suggests that some of this durability can be attributed to these distinctive groupings of highly reactive lime called lime clasts, and they kind of serve as reserves of reactive calcium for pozzolanic reactions over a really long term, resulting in cracks that are essentially self-healing. There's also context for using cementitious materials to improve our natural soil surfaces. So cement stabilized soils are engineered mixtures of in situ soil, water, and cement, resulting in semi-bound to bound material. They're frequently applied to improve subgrade beneath roadways. They can provide significant improvements to the working platform and permanent soil modifications, and they can reduce the need for thicker pavements and potentially increase pavement lifespans. So in their application, the cement is most often applied in a dry condition, but it can also be applied in a slurry form. And once it's spread, it's generally mixed into the subgrade material and then moistened and compacted. And this often takes place in sort of a convoy, so heavy equipment, one after another, performing these steps in sequence. So I think we're kind of drawing from all of these things to try and answer this question of whether there's something in between a natural surface and a traditional pavement that could be used to provide accessible trails while also optimizing costs and sustainability considerations. So can we take what we know about traditional pavements, natural surfaces, pozzolanic reactions, and soil stabilization to sort of use Mazama ash to like thread that needle between the options that are currently out there? So I think there are a lot of challenges in answering that question that CJ is going to talk about.
All right, thanks. Yes, the challenges were many. The first was really batching and processing. So initial studies had suggested we needed to either work with the finer material in the raw ash that we had available or pulverize it somehow to make all of the material more fine. Both of those things sounded labor, time, energy intensive to us. And so ultimately we avoided them. And I'll show you how in a future slide. The other issue we had was on application and logistics. And the previous studies had suggested that topical application was going to pose a challenge. We still had some students who wanted to dig into this, and they produced this wonderful prototype of something that could mix our material into a slurry and disperse it onto the site at a precise rate that was going to be effective at letting it infiltrate into the existing ground. So they made numerous attempts at that, and we quickly realized that if we were going to apply that over a 0.2 mile trail in multiple widths along the trail, it was going to be really challenging, time consuming, and difficult to move material. So we opted for a dry mixing approach that I think worked a lot better. If we get back to the material side of things, here's some of the raw ash material laid out in sieves, and you can see that some of the material is fairly coarse, like a coarse sand, and some of the material, really the ash that we had determined was more active and performed as a pozzolan, was the finest ash that we had. And it would pass, as you can see here, a number 325 sieve. If you're not aware of sieve analysis, a 325 sieve produces something that's about as fine as like a makeup compound. You can barely feel it. It feels very smooth when it's between your fingers. So the raw ash itself, when put through a number of dry sieves, only gave us about 14% of that finest material. But when you run it through a wet sieve or a washed sieve on just the number 325, we could see that 30% of our material was passing that 325 sieve. So that told us that 30% of our raw ash was this fine material that we could rely on to behave pozzolanically. So when it came to batching, we opted to use the 1/3 of active small particles as our pozzolan and assume that the other 2/3 was just inert aggregate that would go along for the ride and be involved in the trail without binding. Here's another look at that in a jar, and you can see working from the number 16 sieve at the bottom up to the 325 sieve at the top. We've got this large to small particle gradation. In the middle, you've got the cat in the hat. And if it's been a little while since you read this, I'll catch you up. The cat in the hat had a number of smaller cats on his head. He made a pink cat ring. It made pink snow. There's a lot of snow in the Pacific Northwest right now. If it had gotten pink, he would employ smaller and smaller cats. And when he got to little cat Z had something called Voom under his hat that did all the work, and it cleaned up that snow. So in the same way, we've got these small particles that are the most active, and that was our goal in working with the ash. You might remember I said we were going to work with a 50-50 ratio of ash to cement. So it's these 1/3 active small particles that we would match in proportion with cement. And that gave us our batch that would give us 3 parts raw ash to 1 part cement. So ultimately, that was our recipe. 3 parts ash, 1 part cement, a trail, and some water. You mix the dry ingredients together so they're interspersed well, spread it on the trail surface, apply water, and move across that surface with a compactor. And that was really our approach for this project after a lot of trial and error with our students.
So our students are really kind of the chefs in the kitchen for a lot of this. I probably can't emphasize enough how much they have contributed to this work. So here you can see some of our students helping us apply some small test patches. In that first figure, they're applying a pre-mixed ash cement mix to the surface in its dry form. And then in step 2, they're raking it in an attempt to integrate it with the in situ soil. Third, they're adding moisture, and then they're finally compacting it with a plate tamper. So we refine these processes through small scale testing like you see here, while keeping in mind that in most applications, we would probably need to be applying the surface over a much larger area. So when we applied our treatment to the Geo Trail last May, we mobilized a crew of about 20 student volunteers and kind of drew inspiration from the convoys that we typically see in roadway construction. So we mixed our dry materials on a much larger scale and used a small front end loader instead of 5-gallon buckets to transport the mix to different areas of the trail. I think we ended up doing about 33 trips back and forth along the trail. Of course, those trips got shorter and shorter the more progress that we made. Behind that, we had a team of students spreading the mix and integrating it with the existing trail surface. And they were followed up by groups who wet the surface and then compacted it with a plate compactor. So in this manner, we were able to resurface our 0.2-mile section over the course of about 7 hours on a Saturday. Overall, we used about 4 cubic yards of ash, 1.3 cubic yards of cement, and about 1 cubic yard of water. And here we return to the results. So the video on the right was taken within a couple of weeks of applying the surface. So you can see that almost immediately there's improvement in terms of visible smoothness of the trail. So I think that really developing an application process that we could actually execute at a larger scale was the beginning of our understanding of the Mazama ash treatment. But it's definitely not the end. So I'm going to let CJ talk about some of the things that we've learned since applications and some of the questions that have come up since then.
All right, the first thing we did, consistent with the prior studies and really as a way of measuring what we had planned to measure, was to look at firmness and stability. And this is based on an ASTM standard and a device called a rotational penetrometer that's produced by Beneficial Designs. The firmness measurement requires the user to stand on the sides of this device and then release the wheel into the ground where a prescribed force is applied and the resistance is measured in terms of the deformation. So how far does that wheel then penetrate into the surface when released straight? The stability measurement then takes the wheel and rotates it a number of times until the measurement stabilizes and you look at the additional indentation. So both of these are displacement measures, and the lower they are, the more firm and stable the surface. So here are some of our results, working on the left from a treated and smooth surface to the right untreated surface. And you'll see we also looked at treated and inconsistent and treated and loose patches. Ultimately, the implementation was fairly inconsistent. We had areas where there was plenty of moisture. The plate compactor created a nice smooth surface that seemed to appear and remain solid for a longer period of time. There were other areas that were just rougher. They were treated, but they were inconsistent. And then there were some areas where it was clear that moisture hadn't really penetrated or been integrated as well as it maybe ought to have. And that was the treated loose material. So you can see here that at the 0.3 inch level, and the blue bars, that's the firmness measure. And so really all of these areas were considered firm. We didn't have any in the moderately or not firm areas. As far as stability goes, it stands to reason that the untreated surface was less stable, that as you might rotate a wheel on that surface, that you would move more material and that wheel would drop farther into the surface. And so you can see that. And even with that, it's still considered stable. So the fine aggregate that was there really was sufficient to provide enough stability when it was integrated with the soil. And we had a reasonably good trail to begin with. But as the prior research has shown, and this really backs up, when we add this ash cement mixture, we do improve the stability effectively by binding that surface material. And so you can see that orange bar falling below or really farther down the y-axis. We also wanted to look at surface roughness. So somebody mentioned smoothness as a factor, and it certainly is. And in fact, there's a measure called the Wheelchair Pathway Roughness Index and an associated ASTM standard. But that standard really relies on a laser measurement of roughness. And so it's actually inappropriate for something like this with loose material on the surface. It's really intended for pavers or sidewalks or places where there might be gaps that would cause roughness. So for a variety of reasons, we didn't measure this, but we did go out to try and measure relative elevations along the length of this and kind of get around the aggregate. And you can see the blue line here is relatively smooth location to location. We took measurements every 10 centimeters, so you can see where those kinks are. The changes in elevation are relatively small, but as you get into the rougher and even the untreated material, you can see where those changes in elevation are more significant. So it was pretty clear that we had made improvements in smoothness. But all of the things that were positive about this trail really started to degrade. And I want to show you a timeline that shows us what happens over the course of about 6 months, 7 months with this project. So these are less than a month after implementation. And you can see here on the left photo that we've got a relatively smooth, consistent surface. And that was true in a lot of places along the trail. There were other places where, again, you can see the aggregate is exposed, it looks looser, and there were spots where the material simply wasn't bound as well as it could have been. If we move into June, we did have quite a bit of moisture in our spring this year. So there was some additional wetting, maybe some additional moisture helping us bind material. But we did start to see lots of use. We didn't close the trail and it wasn't allowed to cure in any meaningful way. So people were active on the trail right after the implementation. And you can see how some of this is breaking down. This photo is right at the start of the trail, and you'll recognize that bench there in another photo. A little farther down the trail, you can really see how some of the well-bound material created a surface crust. And this is something we were concerned about at the beginning of the project. We had other trail managers interested in the project, but they were concerned that this might occur because we're hardening a surface and we're leaving softer material beneath it. And as we weren't too sure what would happen and how deep we would be able to implement the treatment, we opted to try this, try it anyway. And you can see now at the start of that trail and getting later into the year, we do have more degradation of that surface. So as well as some of this material was bound in spots, it's simply not strong enough to stand up to foot traffic, wheeled vehicles, and that sort of thing. Getting into the winter after some snows, some freeze thaw, is detrimental to pavements of any kind. We've got further deterioration. You can start to see some of the native soils appearing where the trail surface has really broken down. And then still farther into the winter, a lot of the soils here are also expansive in nature. So if they go through wetting and drying cycles, they tend to fluff. And so it's pretty clear that there are some challenges with this location, with this binder, and it's not quite right. But we think we solved a lot of problems in terms of batching and placing, but we want to now look at a lot more of these issues, primarily water, distribution of water, depth of penetration, and mixing. We had organics on the trail that may have played a role in weakening certain sections. We certainly want to look at the aggregates and the size of aggregate that's on the trail or incorporated into the surface. And then the soils themselves there will play a significant role. We're integrating this binding material with native soils. The soils we have here are really silty loams, and that's relatively fine material, again, expansive. So it played a big part. And then the seasons with wetting and drying are going to be different in different locations regionally, but here that's a really significant factor.
So I think the main takeaways from this work start with the idea that ash sand cement is a cementitious binder, but it tends to perform differently in different conditions. So it's heavily dependent on things like soil composition and conditions, moisture levels, and uniformity. And we didn't control any of those aspects in this implementation. So we think that the inconsistency in our results probably reflects that. We did develop a treatment process that's feasible over relatively long sections. So I think we accomplished our goal of scaling up our application technique. However, I think that feasibility does come into question when you consider how often maintenance or reapplication might need to take place. Mobilizing a crew of people and equipment might be feasible for a one-time application, but becomes less so if reapplication needs to take place frequently. But even so, we think that treatment is promising for probably very particular conditions. And we aren't yet sure what those particular conditions are. So we need to move forward on this and consider things like deeper treatments and in different aggregate bases and all of these additional conditions as we move forward. So we're continuing to explore these things. Some members of our team have conducted some preliminary studies in effort to characterize the soil at the Geo Trail. A CBR test showed that soil samples with a layer of ash treatment had higher load capacity than the control, which contained just untreated soil. And we're looking at the potential of using mobile devices to better characterize the trail surface, particularly things like utilizing cell phone-based accelerometers and LiDAR sensors to better measure surface roughness. And we're trying to weave all of these things into the experience of our undergraduate students. So like CJ said, Oregon Tech prides itself on providing its students with a really hands-on educational experience. So involving them in this project has been a fantastic way to introduce our students to real research questions, with real solutions that we can take into the real world to apply. So for the past 2 years, this project has been the basis for our Intro to Engineering class. Last year, the first year students helped us really a lot with answering the questions of how we could apply the surface at scale along the geo trail. And this year they're helping us answer the questions of why the trail performed the way it did and how we can improve it. So it's been a really great opportunity to get them involved and out into the field. So this project was grant number 1529 funded by NITC. So we'd like to express our deepest thanks to NITC for supporting this work and for hosting this webinar for us. We would also like to thank all of you for taking the time to join in today. So if there are any questions, CJ and I are more than happy to try to answer them. Thanks a lot.
Great, thanks very much, guys. Great presentation. As they said, go ahead and put your questions in the Q&A box as they occur to you. I'll get us started with a question. What do you see as the major barriers keeping natural pozzolans and locally sourced materials from being used on a large scale, like for mainstream construction projects?
I'll start with that. Maybe Ashton, you can follow up if you want. I think the barriers are really trying to be broken down by a lot of academics trying to find ways of using these materials to offset more carbon intensive materials. So like the previous research by Matthew Sleep here at Oregon Tech was focused on seeing where that material could be used in what proportions to give you reasonable performance in different applications. This is a really challenging application, and it's a really interesting one. So I'm really glad that we had the opportunity to try this, because I think there's still potential. But in many ways, I think a lot of people are being forced to use lower carbon and more local materials as a matter of course as we all adapt to climate change. And I think that's just going to continue. So finding the best ways of using those materials is something we need to continue to focus on.
Are there plans to keep trying to improve on this, make the surface more durable? Do you envision eventually resurfacing more of the geo trail?
I think so. So we definitely have the plans to kind of go back and try and revive those degraded sections of the trail. And I don't think we necessarily yet know exactly what that looks like, whether it's like returning them to their natural state or trying to retreat them. I think we're at the point right now where we've kind of gone back to the small scale test patch approach to really kind of like have a better understanding of those variables that we want to control, whether it's our application technique or the applying it on surfaces of different aggregate sizes. We want to get just really a better understanding of that, I think, before we try to implement again at a larger scale.
Makes sense. And you mentioned the students, the undergraduate students being involved in the research. Could you talk a little bit more about how students were involved in the project? Yeah,
absolutely. So myself and a couple other faculty co-teach our Intro to Engineering sequence. And Engineering 102, we typically run as a very project-based course. So we try to come in with kind of a broader project for the class each year. And so the past 2 years, the theme of the course has been this Mazama ash work. So this class has had between 50 and 60 students for the past few years, and it's actually not just civil engineering students, it's also electrical and renewable energy engineering students. So we try to divide them into interdisciplinary teams. So it might be anywhere from like 8 to 10 teams, and then kind of give them a task associated with helping us meet the broader goals of the project. So each team kind of has a specific challenge of the project that they're tasked with trying to better understand. So for example, this term, we have a group looking at whether different surface application techniques affect the performance of the ash treatment in any way. We have a team looking at doing more field testing of the different mix designs. So we kind of give them a lot of freedom in the course to kind of develop their scope of work around these tasks, but also kind of try to provide a lot of guidance so that they can meaningfully contribute to the broader goals of the project as well.
Great. I do have one more question here in the background, and you may not know this, but I'm just curious. For areas that don't have volcanic ash deposits, what are some natural pozzolans that are commonly occurring and would be possible to use in a similar way?
Their similar ash products come from coal combustion, which I realize is being phased out. We no longer have coal plants in Oregon, but in other locations, like Wyoming has a lot of coal combustion plants. When those plants are scrubbed in their stacks to improve their emissions performance, a fly ash material comes out of that, and that fly ash has similar properties in terms of a pozzolanic behavior, and it's been studied consistent with natural pozzolans.
So is that something that's being used and being developed similar to this?
Yeah, in a very similar way, you can use fly ash to offset cement in a concrete mixture often. I don't know of a lot of applications where it's been used as a soil treatment.
Okay. I guess we will give another minute or so in case folks have questions they want to type into the Q&A box. And then if not, we will go ahead and wrap it up. Oh, toxic components to the ash?
That's a really good question. I think what's interesting about ashes in general is they have a lot of the mineral composition of the parent rock material. They've been burned. In some cases, you look at the loss on ignition, which is how much more material is there that can be burned, and that kind of tells you something about the ash. But in terms of toxicity, it's about as toxic as any other soil that you might find in the area. It doesn't tend to be any more concentrated.
All right, any other questions? Speak now or forever hold your peace. All right, well, I guess with that, we will go ahead and end the webinar. Thanks very much for your presentation, and you guys have a good day.
Thank you all for coming.